Hi guys, this is the Ceyear diode-based USB average power sensor. It features multi-path power detection design and true average power measurement for complex modulated signals. The rugged USB connection makes it convenient for system integration and field use. We connect the waterproof USB cable to the sensor. The other end can be connected to our instruments or a laptop. Today, we use this handheld signal generator to create the signals. The top are the RF output and other interfaces. The compact design can greatly improve the field testing efficiency. We connect the power sensor to the Type-in connector. Then, we connect the power sensor to this handheld spectrum analyzer. It covers up to 54 GHz with maximum 120 MHz analysis bandwidth. We plug in the USB connector. We press Mode to enable the power measurement. The power sensor is automatically identified. After sufficient warm-up, we press Measure 0, External 0, to capture and save the noise level for future detection. After successful zeroing, the noise reading can be lower than minus 73 dBm. We turn on the RF output and set the power to minus 17 dBm. We can see the reading value. We change the out power to minus 60 dBm. Minus 50 dBm. Minus 40 dBm, minus 30 dBm, 0 dBm, 10 dBm, 15 dBm. We set the power to 0 dBm. The pulse period is set to 20 microseconds and the pulse width to 10 microseconds. When the pulse modulation is off, the power reading is about 0 dBm. We turn it on, and the reading now is minus 3 dBm. The current duty cycle is 50%, so 3 dB difference is correct and understandable. We set the out power to minus 20 dBm, and the reading now is minus 23.2 dBm. We turn off the modulation, and the readings are back to minus 20.19 dBm now. We just changed the pulse period to 200 milliseconds, and the pulse width remains at 10 microseconds. We can see the reading is at the noise floor. We changed the pulse width to 100 milliseconds. The power reading is back to minus 23.22 dBm now. There is also 3 dB difference. We keep increasing the width with 10 millisecond steps. We can see the reading is also increasing to minus 20.2 dBm eventually. We can also use the laptop to make the measurement. We connect the USB connector to the laptop and click on the panel shortcut. The panel can automatically detect the device. We click on the device and press connect. The reading is also at minus 20.18 dBm. Now we use the vector signal generator to create a 5G AR signal and test its average power. The signal is 1 GHz and minus 10 dBm. The current reading for this CW signal is minus 10.3 dBm. At random, we select a 100 MHz bandwidth 5G AR signal. We switch it on. We can see the reading is 1 dB lower than the CW signal. We turn off the modulation and then turn it on. The difference is obvious. Actually, this signal generator itself can also support the USB power sensor. We plug in the USB connector. The indicator flashes for several seconds. and then the device is automatically detected. We press System, USB port, USB parameter to enable the testing screen. We can see the current power reading is about minus 10.1 dBm. We quit the power measurement panel, turn on the 5G NR, and focus on the small power reading. We can also see the 1 dB difference. That's all for today's test.